let's go ahead and get started. So what we have today is more usage of the constant acceleration equations, and then we'll do some graphing. I think we should be able to close out your homework number 2 today. That is, by the way, already available. I think that's it for announcements. Any quick questions before we get started? Okay, so here are the constant acceleration equations. I took the liberty of expressing them with the y variables instead of the x variables. So just replaced x's with y's. They work in any one dimension, and whatever dimension you want to call that. If you want to label it x, label it x. If you want to label it y, it's y. Only the x equations appear on the equation sheet that you get for exams, simply because if I wrote all the y equations down, it would take up needless space. You just replace the x's with y's, and that's all you need. 5 equations. Again, the reason why there are 5 is because each one of them lets one of the 5 variables we're talking about take a breather, sitting out, while the other 4 interrelate. And that highly suggests a problem-solving strategy. We already did one example of it last time, but let me remind you how that went. The basic problem-solving strategy is that you're given 3 of 5 variables. That's the minimum number for the system to be completely prescribed. You're asked for a 4th, and you don't know and don't care about the 5th. So you don't know it. It's not given to you in the problem. You're not asked for it, so you don't care. So ironically, that is what allows you, taking that thing that you don't know and don't care about, you pick the equation without it. So it guides you into which one will get the solution done. It will be a one and done situation. If you use the right equation, you should only need 1. So common thing that people do here, not that it's wrong, but it's more work, is that they'll solve for something in one equation and plug it into another. It's not wrong, but you're not taking full advantage of this situation. If you take the answer from equation 1 and put it into equation 3, and then solve for something, whatever that equation is that has those 2 equations combined is already existing. It's on the board. Every single possible algebraic collision has been done. So if you find yourself having to use 2 equations in a single problem, you're using the wrong 2. You should be able to just do it with a 3rd equation that you're not considering and just get your answer right there. Okay? The very first thing, the reason why we changed this to the y direction is because we're doing stuff vertically. So I commonly choose plus y to be upward. And my next example is going to be this. I'm going to have a ball that is launched vertically. I'm going to throw it into the air. Now, I guess let me say a few brief words about throwing. When I'm holding this pen at rest in my hand, its velocity is what?
0.
0. What is its acceleration at the moment?
0.
0. So when I decide to throw something, I accelerate my hand upward, and the pen, of course, goes with it. So it gets an upward acceleration that's applied as long as I'm holding it. Now, what we're talking about is the moment of release. Okay? So when I release it, the acceleration goes from upward in my hand to which way? Downward by gravity. But the velocity, let's say it's 10 meters per second when I am finished at the end when I'm touching it. When I release it and change that acceleration, the velocity is still exactly what it was when it left my hand. So remember, the velocity just before it leaves my fingertips and just after is basically the same. Because even though we've changed the acceleration from being in the hand to not being in the hand, the velocity needs some time to change. So when I say it's thrown upward at 10 meters per second, it means that is the speed at which it's released into the grips of gravity to do something with it. It's going to take gravity some time to bring it to chip that away, so it is going to go up first and then come back down. And so this is going to be what is called a level ground flight. I'll use level ground as just a proxy for saying that the flight begins and ends at the same level. So it leaves my hand and then exits also from flight at the same exact level. Okay? So this is an important special case, and so going to save a little box over here for things that are true about level ground flight. And again, don't take the term level ground too literally. It can be uneven ground as long as you're willing to then adjust your hand to catch it, right? So the point is it enters and leaves flight at the same level. Okay, so let's ask some questions about this. So this is an important system, so let's go ahead and just load up. What's the time to the top? What's the total flight time? What is the, I guess let's call the velocity final. And when I say velocity final, of course, I mean the impact velocity. So just before it hits the ground. After it hits the ground, again, who knows? Depends on the ground. All right, so let's just kind of walk through this. Part A, I'm asked about not the whole flight, but just a subset of it. So we might be wanting to break this down. What we'll call initial is the launch point, and final will be at the top of the flight. So this we're doing not the whole problem, but we're breaking it up into pieces. The first piece is what we're looking at. We'll put down all 5 variables in no particular order. Remember that I have chosen up to be positive, so what would be my initial velocity? Plus or minus? Plus. I'm not always going to ask you when it's a trick question. Sometimes it is as easy as you think it is. Okay. What is the final velocity at the top of the flight? 0. So that represents the turning around point where gravity has finished chipping away the velocity in the upward direction and hasn't yet started to add it in the downward direction. What's the acceleration during this, between the initial and final points? Negative 9.8. So downward is encoded as negative because of my choice of axis. All right. I'm interested in the time between these. This will be the time to reach the top. I don't care about the displacement, although that would be an excellent question. How high does this ball go before it starts to fall? But in this case, I'm not going to solve for it. Which equation would I use? Number 1. So V final y equals V initial. Looks like that. So I solve it for time. T equals V final minus V initial over AY. I can plug in that the final velocity is 0. Of course, the acceleration is a constant. I'll point out, let's just throw in proportionalities here for a second. I notice that the time to the top is directly or directly proportional or linearly proportional to the launch velocity. So that means if I threw it up at twice as fast, it would take twice as long to get to the top, right? So those are the kind of things that proportions let you say very quickly. If you threw it upward 3 times as fast, it would take 3 times the time to reach the top, right? So you can see these relationships. You don't have to just get too bogged down in the specific numbers. So let's go ahead and put it in. If you plug that in, you should be able to get 1.02 seconds. If you get a minus sign there, the ball did not go back into the past. So check your algebra. So that's the time to the top. Any questions on that before I move on to part B? Okay, so let's do part B. Now part B asks me about the total flight time, so I want to know the time like this. So I want to know the time between when it starts and when it ends up back at the same level. Now this has both an upward part and a downward part. So am I required to break it up into two pieces, or can I do it all with just one of these equations? Well, the question you have to ask yourself is the acceleration constant? If the acceleration is constant throughout that time interval, then you can use the equation. Is the acceleration constant here? Yes, it is. The acceleration is always downward at 9.8 meters per second squared. The velocity might be upward and then downward, but it's all happening under the exact same constant acceleration, so you can apply the equations over this whole thing. We saw that before, this idea that acceleration can first stop a velocity, turn it around. That can all happen under constant acceleration. So let's, again, put down our variables. My initial velocity, well, I haven't changed the initial point, so that's still plus 10. This entire thing does happen under the same acceleration. Can I say the final velocity is 0? No, because gravity would never stop something on the way down, right? This is not 0. In fact, that's the impact velocity we're going to look for in part C, but we don't care about it right now. Remember, gravity is able to stop you while you're going upward, but gravity would never stop you as you're falling. That's the ground. So make sure you understand why we can simultaneously set this to 0, because that happens under gravity only. Remember, this is your contract with the problem. The gravity is the only influence. No hand, no ground, no air resistance. That's gravity only. Gravity will bring something to a stop at the top of the flight. Gravity would never bring it to a stop as it's falling. All right, we need one more thing. We want the time, so I guess looking at this, it's the displacement that we know. What's the displacement?
0.
0, because you stop and end at the same place. So you haven't gone anywhere in the long run. Remember, displacement, that's the beauty of displacement, right? It doesn't care about what you did, it just cares about the endpoints. Now you might ask, how does it account for the fact that you didn't just stay there? You went up first and then went back down. Well, it is accounted for because if you start with an initial positive velocity and a negative acceleration, you're going to move. It's just what happens is in the equations accounts for the fact that the acceleration chips away the velocity, stops it, turns around, and brings you back to the starting point. All right, which equation do we use? Number 2. So, looks like this. Now this one I'm not going to solve for the variable of choice in terms of before I plug in the numbers, because I want to make a point, a general point about the solution. So I put it in, I get 0 equals plus 10 times t plus 1/2 negative 9.8 times t squared. Now if you have to solve an equation where both the variable squared and not squared appears, that's when you should start thinking, at least in the back of your head, I might have to use the quadratic equation. It's not necessary in this case. You kind of get lucky that it's not, but that's not always going to be the case. The reason why you don't have to here is because you get lucky that the displacement was 0. You got lucky that it was a level ground flight. 0 being the great absorber that it is, if I divide both sides by t, of course 0 divided by t is still 0, and so I haven't just sloshed my problem over into the denominator of the other side. But over here, the t cancels entirely here, and one of them cancels here. So I can actually get away with not using the quadratic equation. In fact, if you solve here, you should get t equals 2.04 seconds. So again, try it at home, make sure you can get that. And there's something I want to point out here. The time happens to be exactly twice of the top time to the top, right? So apparently it took 1.02 seconds to reach the top, 1.02 seconds to fall, for a total flight time of 2.04. This is actually a general truth about level ground flights. T up equals T down. It's completely symmetric to rising and falling. It'll take the same amount of time to go up as to come back down. Now, if you need motivation for why that is, just think about what's going on. If I go ahead and I sketch in the velocities will be upward, getting smaller, going to 0, coming back, getting faster. The only difference between going up and coming down is that when your velocity is upward, your acceleration is against you, so it's slowing you down. Whereas when you fall, the velocity and acceleration are in the same direction, so it's going to speed you up. That is the only difference. It's completely symmetric otherwise. So it's going to take the same amount of time to slow you down to a stop as to then speed you up on the way down. And in fact, this is kind of previewing part C. We're going to find that it not only takes you the same amount of time to fall back down as it took you to go up, and you're going to reach the same speed. So here, you're going to go from 10 meters per second to 0. And from here to here, you're going to speed up from 0 to minus 10 meters per second. It's no surprise because it's the same exact acceleration that's guiding both of those. The only difference being the acceleration might be constant, but it's working against you on one half and it's working with you on the other half. Okay? Now, I certainly didn't prove it in general, but if you solve this symbolically, you would find that it is true in all cases, not just a specific launch velocity. If you throw it faster, it'll take more time to stop it, and it'll climb higher in that time. But then by the time you fall back down to the same level, you'll have recovered all your initial speed in the other direction, and it'll take you the same amount of time to fall back down. Okay? And I guess the other thing I wanted to address is when do you have to do the quadratic equation? So that's something that I'll address in, I guess, I'll do that in the next example. So I'll get to that in just a moment. I guess let me go ahead and do part C here, just to complete the problem. Part C, of course, is exactly the same setup as part B. We are asked about the very end, so the final point is in the same place. The setup is exactly the same. I can go ahead and solve for, I use the same givens, 10, 0, negative 9.8. The only difference now is I'm solving for something different. And again, you might say, why am I ignoring the time? Didn't I just solve it in part B? Well, it's reassuring to know that I could walk up and do part C first, isn't it? They don't have to be all done in this order. Which equation would I use for this? Number 3, right? The one missing time. Let me show you what happens there. There's a little bit of a fluke to be aware of in that equation. Looks like this. Well, the displacement is 0, so that's going to kill this whole term, right? So we get this. We get the squares of the initial and final velocities are equal. Does that mean that they are equal? No. 1 is not equal to negative 1, but their squares are equal, right? So there could be, as any time you take the square root, there could be a plus or minus sign hiding out underneath there, and as far as this equation goes, it can't mathematically make the distinction, but your common sense can make the distinction. So do you think the final velocity is still upward or is downward? It's downward, right? So I picked the minus sign because that just makes sense, even though the equation mathematically can't do that. So this is another fact about level ground which we mentioned. Once you return to the same level, you'll have the same speed, but opposite directions. So the velocity will be equal and opposite. By the way, if you scan around these equations, you might ask, well, how often do I have to worry about that? Only equation 3. Because any of the quantities that could be plus or minus, they never get squared anywhere else, right? There's no other squares here except for what? What's the other quantity that's squared here? Time. But time there's never a negative time. So if you solve for t squared and take the square root, you never have to worry if there's a negative hiding underneath. You know there can't be. Okay? So if you take the square root and forget that it could be plus or minus, it's kind of ignorance is bliss, right? Because you would kind of naturally pick the positive, which is correct. But here, we should pick the negative. Okay? So these are things about level ground that come from the symmetry of the situation. Just the idea that the same acceleration is guiding the whole flight. It just slows you down on the way up and speeds you up on the way down. Okay? So if these are the velocity vectors, remember that the acceleration is always downward, which means it will be against your velocity rising and with your velocity falling. Okay. Any questions before I move on to the next example? Okay, so next example, not going to be that involved at this point. These are all just variations on a theme. So I just want to ask in this next one, just the question that might be the most tricky. So this is a non-level ground problem. This is a problem in which you walk up to a cliff, you launch a ball vertically, and when it comes back down, you pull your hand back so it can continue to fall. Let's say that your this launch speed, which leaves your fingertips, is 5 meters per second, and the amount that it ends up falling is 30 meters. And I'm going to ask you for the time of the total flight time. So, if you've seen physics before, there's definitely a crowd of people, I call them the multiply by 2 crowd. Any flight you give them, what they want to do is calculate the time to the top, multiply by 2, and that is correct if you happen to have level ground. But that approach is not going to work here. The time to go up and the time to come down are highly asymmetric, right? You spend a lot less time going up and a lot more time falling because you fall further than you rise, right? So this is where the multiply by 2 crowd starts to get into breaking the trip up into a bunch of different pieces. And again, it's completely not necessary. This whole thing happens under constant acceleration. So I would say just do the whole thing at once. Set the initial point here, final point here, and that's all we need to do. Let's do it. So I'm going to choose again, as I usually do, plus y direction to be upward. That means my initial velocity is plus 5. What's my acceleration? Negative 9.8 the whole time. On your way up, on your way down, the whole thing. That's the acceleration. Can I say the final velocity is 0? No. Gravity doesn't stop you. That final velocity would represent the impact speed that gravity would have a chance to give it. We're looking for the flight time. Is the displacement 0 now? No. What is it? Negative 30. It's negative because the displacement, which connects the beginning to the end, is a downward displacement, and I've chosen up to be positive. So don't forget that minus sign. Okay? Every single quantity, the first 4, you should consider if they're plus or minus. They all have the ability to be plus or minus, only time is positive, always. So which equation do I use? Number 2. Same as the last example. Here's what you'd get though. You get minus 30 equals plus 5t plus 1/2 negative 9.8 t squared. And there is no way you can slosh the terms around to isolate t, okay? You can try it. You'll be there all day. If you think you did it, you made a mistake. You surely can't, okay? So this is an occasion where you have to employ the quadratic equation. There is no other way to isolate t. Now, Why didn't we have to do it before? We got lucky that there was a 0. We had 0 displacement, but here 0 is replaced by minus 30. So if I divide both sides by t, I haven't solved my issue. I have minus 30 over t on that side. What do I do with that? So let me say a few brief words about when the quadratic is necessary. And I should say there are tricks to get around it, but let's say when the quadratic equation is the easiest way, right? When other methods would be even more convoluted, using the quadratic equation is not the worst thing in the world, but you don't want to have to use it if there's an even simpler way. Number 1, when you're solving for time. Why is that? Mathematical fact of looking at our 5 equations. There is only one variable that appears both squared and not squared in any single equation, right? And by the way, it only occurs squared and not squared in 2 and 5